What if I told you that magnetic forces might not be real, or that what you think about magnets is just an illusion? Magnets seem so simple, right? But there is something deeper going on, something which actually led Einstein to the discovery of theory of special relativity. In this video, we will peel back the layers of what magnetism really is and explore a mind-blowing idea that the magnetic force is nothing more than a clever illusion of physics, a trick played by the universe. Are you ready to challenge everything you thought you knew? Let's dive in. In your childhood, you must have played with magnets. Looks and feels like metal, which sometimes stick together magically, but sometimes refuse to even get close. And if you notice, you can find these in day-to-day appliances like loudspeakers and fridge doors. And by this age, you must have noticed that some metals can be permanent magnets, such as iron, but some can't, such as copper. However, if you pass electric current through any metal, it behaves like a magnet. And this is how any motor, such as a fan, works. Wait, what? How? And most importantly, why? Here comes Einstein with the reason. In June of 1905, Einstein wrote a paper which shook the physics world from the grounds up. Maxwell's equations of electrodynamics and Newton's laws were not compatible. So Einstein came up with what he called electrodynamics of moving bodies, which later most commonly known as special relativity. Special relativity suggests that in our universe, while these items are invariant or absolute for everyone, these items are relative, and they are perceived differently by observers moving relative to each other. In this video, we are going to use these three: charge, which must remain same no matter how many frame of references we change to; space and time, which are going to be different for observers moving relative to each other. This is a direct contradiction for Newton's laws of motion. For example, if you notice carefully enough, you will find that time passes slowly for observers moving relative to you. So if I ask you, when did your friend's plane leave? Since your friend is moving relative to us, both of your answers will differ. And moving objects are also contracted in their direction of motion, and so does distance between them. However, only when seen from your frame of reference. When you switch frame of reference to the plane, we both on ground will look contracted and slim now. This change of frame of reference is very important concept. This is what special relativity is all about. How much contraction is given by this equation and is dependent on the relative motion between the objects. So when you see from your frame of reference, you notice that the plane is looking slim. Your friend, however, will report that everything looks normal there in the plane. And it's you guys on the ground who are looking slimmer. So what does this have anything to do with magnets? Imagine a copper wire. It consists of positively charged ions and negatively charged loosely bound electrons. The number of these positive ions are same as the number of free negative electrons. So the wire is neutral and does not have any charge. That means if you shrink me to the size of these particles, add a positive charge on me, and put me near the wire, I would experience no force from the wire at all. Now you started electric current in the wire. The electrons will start drifting in the wire. However, if we take a tiny section of the wire, we will see that the number of electrons and positive ions are still the same in that section, meaning the charge density remains constant and I will experience no force. But what happens when I start moving? And to keep things simple, I start moving with the same velocity as electrons. Well, in your frame of reference, the wire is still neutral and as per you, I should not experience any electric force. On the other hand, I am experiencing something very different. When we change the frame to my perspective, you and the positive charges in the wire will be moving from my frame of reference. So according to special relativity, the separation between those charges will be ever so slightly contracted compared to your perspective. Remember the friend in the flying plane example? Also, from my perspective, since I am moving with the electrons with the same velocity, they won't be moving anymore. So they will be more spread out in my perspective compared to your perspective. Remember the flying plane example? When we changed the frame of reference to the plane, it looked normal and not contracted. These two changes together means there is a higher density of positive charge in the wire. So it's no longer neutral. It has more positive charge than negative charge at any given section, which makes the wire positively charged. And since I am also positively charged, I will feel a repulsive force from the wire and move away from it. Forces may be relative, but events are not. So I must also move away from the wire when we are watching from your frame of reference. But in your perspective, this seems mysterious. Let's change frame of reference back to you to understand this. Even though there is no force on me when I am not moving, when I move, however, you see me getting repelled from this neutral wire. How do you explain that force? Well, you say that it is the magnetic force because you know that a wire with current deflects a permanent magnet. So really, this experiment shows that a magnetic field is just an electric field from another frame of reference. In your frame, you say I am moving due to a magnetic force. In my frame, however, I am actually moving due to an electric force. One thing to note here, even though the drifting velocity of electrons is extremely low compared to the speed of light, the sheer number of electrons and positive ions make up for it, and we get a noticeable force. But wait, how does this explain force on a moving charge without a wire? Well, if you put two charged particles having same charge, they will repel each other as per this law known as Coulomb's law. If you move them, however, you will see them getting apart slowly compared to what you were seeing when they were static. And you are going to conclude that this is due to the induced magnetic field, which is opposing some of the repelling force. However, let me shrink again and get in the same frame as the moving charges. From my perspective, both charges are still, so I should see the same force given by Coulomb's equation, which you saw when the charges were static in your frame. Wait, but how come you are seeing them getting apart slowly, but I see them getting apart at usual rate? You see, Einstein comes to rescue again. Remember our friend in the flying plane example? He reported that less time has passed in his watch. That's because time passes slowly for a different frame which is moving compared to us. Since these charges and I are moving, when you look at us, our time will appear slow to you. And that's why you see the charges getting separated slowly. However, as usual, when using Einstein's relativity, there will be some paradox. There seems to be two of those here. One is why the wire does not get negatively charged because of electrons getting compacted when the current starts flowing in your lab's frame. Because moving electrons should get compacted, right? Second is that when we switch frame to me, who is shrunken down and moving with the electrons, where does this extra charge on the wire is coming from? Because as we know, charge is absolute and it does not depend on the frame of reference. Can you figure these out? Comment down below if you want me to explain this in a future video. Also, you must have noticed up until now we did not talk about permanent magnets. You might be asking, well, how does those work? You will be excited to know that those are even more interesting and will be explained with quantum mechanics, which I am planning to explain in a future video. These magnets, along with electricity, are extremely useful to humans, as you might imagine. We can use those to transmit data over what's called electromagnetic waves. One very commonly used example in our day-to-day life is Bluetooth. In this video here, we discussed and understood harms of Bluetooth radiation, as it has the same frequency as microwave ovens. Click on this video here and hopefully I will see you there. Thank you so much for watching, and if it was worth your time, do consider subscribing.